On behalf of Panimala Institute of Technology, AICT pre-run a GATE training program for EC and EEE students in the subject Signals and System. We welcome you all once again for the topic Dtft. The previous lectures we have discussed about various topics of signals and system, that includes classifications of signals, classifications of system. Then we have also seen what is Fourier series, Fourier transform, and we will be discussing about discrete time Fourier transform in this lecture. So Dtft, the discrete time Fourier transform provides extremely useful representation for periodic sequence. Often, however, we need to deal with the sequences that are not periodic. So in this case, Fourier series, discrete Fourier series is not applicable. So a more general tool than Fourier series is needed in this case. The Fourier transform can be used to represent both periodic as well as aperiodic sequence. Since the discrete time Fourier transform is essentially derived from the discrete time Fourier series through a limiting process, the Fourier transform has many similarities with a Fourier series. So that is the main motivation behind starting of discrete time Fourier transform. And we all know that we initially saw with Fourier series, which is only applicable for the periodic signals, and then we had moved on to the Fourier transform. Now we are discussing the extract from the Fourier transform, a specific case for discrete time Fourier transform. Then we will be discussing about discrete Fourier transform, and from that it has emerged to the fast Fourier transform. To say in brief, Fourier series, Fourier transform, Dtft, and the discrete Fourier transform, what will be in terms of time domain and in frequency domain. Fourier series, it is a continuous periodic, and in time domain it is x of t, and it is continuous periodic, and in frequency it is discrete infinite, we have ck. Fourier transform, continuous infinite, x of t. Frequency, again it is continuous infinite, x of omega. Discrete time Fourier transform, discrete infinite, x of n. Continuous periodic, x of e power j omega. Discrete Fourier transform, discrete finite periodic, x of n. Again here it is discrete finite periodic, x of k. So this is what we were giving you, the comparison of Fourier series, Fourier transform, discrete time Fourier transform, discrete Fourier transform with respect to time as well as frequency. So please do remember this when we will be using Fourier series, when Fourier transform is used for what kind of signals. Discrete time Fourier transform and discrete Fourier transforms are used. So next we will discuss about the development of Fourier transform. The discrete time Fourier series is an extremely useful signal representation, but unfortunately the signal representation can only be used for periodic sequences. Since frequency of the periodic Fourier series is inherently only for periodic. When we have aperiodic signals, Fourier series fails. Many sequences are not periodic, however, because most of the signals are aperiodic signals that we face in the real-time scenario. Rather than abandoning Fourier series, one might wonder if we can somehow use this Fourier series to develop the representation that can also be applied for the aperiodic sequence. So by viewing an aperiodic sequence as the limiting case of n periodic sequences where my n tends to infinity, we can use Fourier series to develop a more general signal representation that can be used for both aperiodic and periodic sequence. This more general signal representation is called as discrete time Fourier transform. This is how the discrete time Fourier transform came into existence. The main drawback of discrete time Fourier series is it is only applicable for the periodic signal. However, most of the real-time signals are not going to be periodic in nature. So to make it as a generalized, instead of abandoning the Fourier series, we went for viewing the aperiodic sequence as a limiting case of a n periodic sequence where my n tends to infinity, and we can use this Fourier series itself as a generalized signal representation which can be used for both periodic as well as aperiodic sequences. So this is how the development of Fourier transform came into the existence. And to recall the Fourier series representation of an n periodic sequence, x is given by x of n is equal to summation k is equal to n 1 over n summation l is equal to n x of l e to the power minus j 2 pi divided by n kl into e to the power j 2 pi by n kn. So in this above representation, if we take the limit as n tends to infinity, we will be obtaining x of n is equal to 1 by 2 pi integral 2 pi summation n is equal to minus infinity to plus infinity x of n e to the power minus j omega n e to the power j omega n d omega, where this term is x of omega as we know already. Since n tends to infinity, two finite summation becomes an integral and infinite summation. So this is a more generalized function representation of Fourier transform. So I can define the Fourier transform of the sequence as, and it is denoted by fx, or in general we call it as x of omega. The discrete time Fourier transform is given by x of omega, which is equal to summation n is equal to minus infinity to plus infinity x of n e to the power minus j omega n. And the preceding equation is sometimes referred as Fourier transform analysis equation or forward feed Fourier transform equation. So we can have this equation as analysis equation and forward Fourier transform equation. And the inverse Fourier transform is denoted by f inverse x or x of n, which is given by 1 by 2 pi integral to pi x of omega e to the power j omega n d omega. This is what we have derived in the previous slide. And this equation is called as synthesis equation. This is called as synthesis equation or inverse Fourier transform equation. So both these equations combined together, we call it as Fourier transform pair. Both this equation combined together, we call it as Fourier transform pair. So and in general we can rewrite it as x of n Dtft x of omega. So if we take forward transformation, we obtain x of omega for x of n. If we take inverse Dtft for x of omega, we obtain x of n. So in general, we call this both equations as Fourier transform pair. So the equation for Fourier transform, discrete time Fourier transform is x of omega is equal to summation n is equal to minus infinity to plus infinity x of n e to the power minus j omega n. Inverse Fourier transform, x of n is equal to 1 by 2 pi integral x of omega e to the power j omega n d omega. So these two formulas we will be using for obtaining the Fourier as well as inverse Fourier transform. So for a sequence x, the Fourier transform analyzing equation, therefore as discussed in the previous slide, x of omega is equal to summation n is equal to minus infinity to plus infinity x of n e to the power minus j omega n converges uniformly if summation k is equal to minus infinity to plus infinity modulus of x of k is less than infinity. Therefore x is absolutely summable. For a sequence of x, the Fourier transform analysis equation, therefore x of omega is minus infinity to plus infinity x of n e to the power minus j omega n converges in minimum square error sense if summation k is equal to minus infinity to plus infinity modulus of x of k the whole square is less than infinity. So x is square summable. So we have seen x is absolutely summable if k is minus infinity to plus infinity summation modulus of x of k is less than infinity, and similarly k is equal to minus infinity to plus infinity summation modulus of x of k the whole square is less than infinity. It is square summable. So for a bounded Fourier transform x, the Fourier transform synthesis equation x of n is 1 by 2 pi integral x of omega e to the power j omega n d omega will always converge, since the integration interval is going to be with respect to the finite duration. Now we will see the properties with the time domain as well as frequency domain. Linearity property, translation property, modulation, conjugation, time reversal, upsampling, downsampling, convolution, multiplication, frequency domain differentiation, differencing, accumulation. So as all the cases we know that this is not going to change, whereas the transformation is only going to differ. So either it may be a Laplace transform, or it may be a Fourier transform, or a discrete time Fourier transform. Whenever we say the term linearity, the next moment it should come into your mind that a1 x1 of n plus a2 x2 of n. And in the frequency domain, we will get a1 x1 of omega plus a2 x2 of omega. Similarly, translation, or sometimes we call it as shifting property, x of n minus n naught, which is e power minus j omega n naught x of omega. Modulation property, e power j omega naught n into x of n is x of omega minus omega naught. Conjugation property, x star of n, x star of minus omega. Reversal property, x of minus n, x of minus omega. Upsampling, x of n, x of m omega. Downsampling, m, x of n, 1 by m, summation k is equal to 0 to m minus 1, x of omega minus 2 pi k divided by m. Convolution, always as discussed, convolution, time domain convolution, multiplication in frequency domain. The vice versa. Multiplication in the time domain, convolution in the frequency domain. Frequency domain differentiation, n into x of n, j d by d omega of x of omega. Differencing, x of n minus x of n minus 1, 1 minus e to the power minus j omega x of omega. Accumulation property, summation k is equal to minus infinity to n x of k e to the power j omega divided by e to the power j omega minus 1 x of omega plus pi into x of 0, summation k is equal to minus infinity to plus infinity del of omega minus 2 pi k. So we do have this generalized property along with 4 other properties like periodicity, Pascal's relations, even or odd symmetry, real conjugate symmetry. The periodicity property, x of omega is equal to x of omega plus 2 pi. Pascal's relation, minus infinity to plus infinity. Modulus of x of n the whole square is equal to 1 by 2 pi integral 2 pi modulus of x of omega the whole square d omega. Even symmetry, x is even and the other capital X is also even. Similarly, x is odd, the capital X is also odd. Real conjugate symmetry, x is real, x will be conjugate symmetry. So this properties we should also know. And now I will give you the basics discrete time Fourier transform pairs. X of n, del of n, 1 u of n, a power n u of n, minus a power n u of minus n minus 1, a power modulus of n, cos omega naught n, sin omega naught n, cos omega naught n u of n, sin omega naught n u of n, b by sin bn, u of n minus u of n minus 1. So generalized formulas we have given. If you want, even we can try to solve one problem and show you. Say example, let me take the case of del of n. As we know the formula for Dtft, first you have to be very thorough with the formula of Dtft. What my Dtft says is my x of omega. So x of omega is given by summation minus infinity to plus infinity. Summation n is equal to minus infinity to plus infinity. X of n e to the power minus j omega n. So this is a known fact for us, and instead of x of n I am going to substitute as del of n. I am substituting here del of n. Now what happens when I put del of n here? Del of n exists only at n is equal to 0. So when I put n is equal to 0, I will get del of 0. Del of 0 is 1. E power 0 is 1. So the answer is going to be 1. Similarly, we can find for all the other cases also. I will just take one more example and I will explain it to you. A power n u of n. We will check this. And this is all very important thing to be noted. If the problems are going to be asked with respect to discrete time Fourier transform, if you know this transformation pair, you need not solve it and find it. Just keep remembering the answers. It is easy for us to do it. So again, by the formula of x of omega, we can write it as summation minus infinity to plus infinity. Summation minus infinity to plus infinity x of n e to the power minus j omega n, e to the power minus j omega n. Now here it is given as, I will try to use pointer or something else. Here it is given x of n to be, we are assuming a power n u of n. So what I do was a power n u of n. So the limit can be changed to 0 to infinity. Limit will be changed to 0 to infinity. Again the same issue is occurring here. I will use the same. A power n u of n, 0 to infinity becomes e to the power minus j omega, e to the power minus j omega n. Now what I do is I group this thing. So I will have a e to the power minus j omega whole to the power n. Now the summation value 0 to infinity, we all know by this, which is given by 1 over 1 minus a e to the power minus j omega. So this is the answer. So if you want to make it in the positive way, you multiply and divide by e power j omega. So I will have e to the power j omega divided by e to the power j omega minus a. So I have obtained the answer for this. Similarly, we can find it for minus a power n u of minus n minus 1, which is given by e power j omega. Same answer you will get, whereas the modulus of a here is less than 1, here modulus of a is greater than 1. Same thing can be applicable for a power mod n as well as. You can find it for this case also. 2 times you have to solve it and find the answer. So these are all very important things to be noted. Similarly, we can derive for cos omega naught n, sin omega naught n, and all these cases are possible. Now let us move to the periodicity concept. So by the definition, x of omega is given by summation n is equal to minus infinity to plus infinity x of n e to the power minus j omega n. I am just trying to prove the periodicity property, and for all integers of k, we know that periodicity property, it should satisfy x of omega plus 2 pi k. Now I am just going to substitute instead of omega 2 pi k. So what happens here? Summation minus infinity to plus infinity x of n e to the power minus j omega plus 2 pi k into n. Now I am bringing this n inside. I will have e to the power minus j omega n plus 2 pi kn. So as we know earlier, e power minus j 2 pi kn value is 1. Always remember this thing, e power minus j 2 pi kn value is 1. How it is? Because e power minus j 2 pi kn can be written as cos 2 pi k n plus j sin 2 pi kn. Any of that whole term cos 2 pi and sin 2 pi term will become 1. So with that, we come to the conclusion that summation n is equal to minus infinity to plus infinity x of n e power minus j omega n. So which is equal to x of omega. So Fourier transform of x of a sequence x is always 2 pi periodic. So this is a periodicity property, linearity property. as discussed, if x1 of n dtft, if x1 of n dtft is x1 of omega and x2 of n dtft is x2 of omega, then a1 x1 of n plus a2 x2 of n dtft is a1 x1 of omega plus a2 x2 of omega. The same thing can be also solved as discussed several times for all the other transformation. Just substitute here a1 x1 of n plus a2 x2 of n, we will have e to the power minus j omega n. So you can split this summation. First summation will have, you can take a constant a1 outside. Here it is x1 e to the power minus j omega n. Similarly, the second case you can take a2 outside. I will have summation x2 e to the power minus j omega n. So this is similar to x2 of j omega. See the same resemblance, x2 of omega, and this I can write it as x1 of omega. So I will have a1 x1 of omega plus a2 x2 of omega. So this is what I have obtained here. Linearity property, translation property or shifting property, the same thing can be also derived. What I do here is summation minus n is equal to minus infinity to plus infinity. Summation n is equal to minus infinity to plus infinity. I take, sorry, I just substitute it here into e to the power minus j omega n, e to the power minus j omega n. Now what happens, let me assume some dummy parameter m is equal to n minus n naught. M is equal to n minus n naught I am assuming. So when I assume this, from this n can be rewritten as m plus n naught. M plus n naught I will be having. Then just substitute it here in this equation. So I will get x of m e to the power minus j omega. Instead of n, I will put m plus n naught. So you can split this integrate summation and into two, this e power exponential into two parts. So I take e power minus j omega n naught outside. Remaining term is x of omega. So very simple thing, but you have to know the basic fundamentals. Easily you can solve this property if required. Next, modulation property. If x of n discrete time Fourier transform is x of omega, then e to the power j omega naught n into x of n is x of omega minus omega naught. So again the same property can be proved. So I am not solving it, I am leaving it to you. Conjugation property. If x of n dtft is x of omega, then x star of n dtft is x star of minus omega. Going to the next property, time reversal. If x of n dtft is x of omega, then x of minus n dtft is x of minus omega. If you want, you can try to solve this. Very simple, similar to all the other properties. Please do remember, properties are very important, vital role in solving gate problems. So do remember this properties all. Upsampling. If x of n dtft is x of omega, then upsampling m into x of n is x of m omega. This is the upsampling property. Downsampling property. If x of n dtft is x of omega, then downsampling m x of n dtft is 1 over m, k is equal to 0 to m minus 1, x of omega minus 2 pi k divided by capital M. Convolution. As discussed in several times, time domain convolution, frequency domain, it is going to be multiplication. Similarly, we will have the vice versa also. If x1 of n dtft is x1 of omega and x2 of n dtft is x2 of omega, then x1 of n convoluted with x2 of n dtft is x1 of omega into x2 of omega, and this is known as convolution or time domain convolution property of Fourier transform. So we should not always remember that time domain convolution will be multiplication in the frequency domain. This should be remembered always. So this suggests that Fourier transform can be used to avoid having to deal with convolution operation. Very simple case that everyone should remember. So again the vice versa case, multiplication in time domain will yield to you the convolution in the frequency domain. So do not forget that the factor of 1 by 2 pi in the above formula. Most of them will not use this thing. You should always remember this 1 by 2 pi. Since the property of Fourier transform is often tedious to apply in the forward direction, as it turns the multiplication into the convolution. So do remember all this case. Next, frequency domain differentiation. If x of n dtft is x of omega, then n into x of n dtft is j d by d omega of x of j omega. Differencing, if x of n dtft is x of omega, then x of n minus x of n minus 1 dtft is 1 minus e power minus j omega x of omega. So most of the difference equation when we are solving, this kind of formulas are always very important to be used. So you can even generalize this x of n minus k, x of n minus k, I can generalize it. I will have e to the power minus j omega k, e to the power minus j omega k into x of omega. So this property follows quite trivially from the linearity and translation properties of Fourier transform. Accumulation property. If x of n dtft is x of omega, then summation k is equal to minus infinity to plus infinity x of k dtft will be e to the power j omega divided by e to the power j omega minus 1 x of omega plus pi x of 0 into k is equal to minus infinity to plus infinity del of omega minus 2 pi k. Parseval's relation, very important relation, which gives you the energy. So if x of n dtft is x of omega, then summation n is equal to minus infinity to plus infinity modulus of x of n the whole square is equal to 1 by 2 pi integral 2 pi modulus of x of omega the whole square d omega. Here the energy of x in the energy of x are equal to up to the factor of 2 pi. This is known as Parseval's relation. Since energy is often a quantity of great significance in engineering application, it is extremely helpful for us to know about the Fourier transforms of Parseval's energy to upscale the factors. Even in the odd symmetry, as I discussed earlier, x is even again, x is odd, here capital X is also odd. Similarly, real sequence, a sequence x is real if and only if the Fourier transform x satisfies x of omega is equal to x star of minus omega for all omega. Therefore, x is a conjugate symmetry. X is conjugate symmetric. Thus, for a real valued sequence, the portion of the graph of a Fourier transform for the negative values of frequency omega is redundant, as it is completely determined by the symmetry. So, from the properties of complex number, one can show that x of omega is equal to x star of minus omega are equal. So, modulus of x of omega is equal to modulus of x of minus omega, and arg of x of omega is equal to minus arg of x of minus omega. So, modulus of x of omega is even, arg of x of omega is odd. So, note that x being a real and does not necessarily impact the x is real. Now, we will try to see the duality between discrete time Fourier transform and continuous time Fourier series. So this is the duality equations. Dtft equation, first equation is Dtft equation, x of omega is equal to summation k is equal to minus infinity to plus infinity x of k e to the power minus j k omega, and x of n is equal to 1 by 2 pi integral to pi x of omega e to the power j n omega not d omega. The continuous time Fourier series synthesis and analysis equations are respectively given by, this is for continuous synthesis equation, this is for the analysis equation. Xe of t is equal to summation k is equal to minus infinity to plus infinity a of k e to the power j k 2 pi by t into t. Similarly, a of n is 1 over t integral t Xe of t e to the power minus j n 2 pi by t into t dt. So which can be rewritten respectively as Xe of t will be equal to summation minus infinity to plus infinity a of minus k e to the power minus j 2 pi k 2 pi by t into t, and a of minus n is also rewritten as 1 over t integral Xe of t e to the power, instead of minus I will have e to the power plus j n 2 pi by t into t dt. The continuous time Fourier synthesis equation with t is equal to 2 pi corresponds to the Dtft analysis equation with x is equal to xe, omega is equal to t, and xn is equal to a of minus n. Again, the CTFC analysis equation t is equal to 2 pi corresponds to the Dtft of synthesis equation x is equal to xe and x of n is equal to a of minus n. Consequently, the Dtft x or the sequence small x can be viewed as continuous time Fourier series representation with 2 pi periodic spectrum x, with the 2 pi periodic spectrum yes. So the Fourier series coefficient sequence A is produced by just sampling xn at integer multiples of fundamental frequencies 2 pi by n and scaling the resulting sequence by 1 over n. The Fourier transform of a periodic sequence can only be non-zero at integer multiples of the fundamental frequency. So this is the main thing that everyone should remember. The Fourier transform of periodic sequence is always do remember these cases. The Fourier transform can be generalized to handle the periodic sequences. Consider a n periodic sequence x, and it is defined as xn of n is x of n for 0 less than or equal to n less than or equal to n, 0 otherwise. If therefore xn of n is equal to x of n over a single period and 0 elsewhere. Let A denotes the Fourier series coefficients sequence of x, and let capital X and capital Xn denote the Fourier transform of similarly x and xn respectively. The following relationship can be shown as x of omega is equal to 2 pi by n summation k is equal to minus infinity to plus infinity x of n 2 pi by k by n omega del of omega minus 2 pi k by n. Similarly, we can get ak and x of omega. So very important thing that everyone should remember. So frequency response of a linear time invariant system, as discussed in the previous case, the same thing holds good here also. Let us consider a linear time invariant system which is having the input x and output y, and the impulse response is denoted by h. So with respect to the Fourier transform, we will have capital X, capital Y, and h denotes the Fourier transform of this x, this y, and this h. So we know that y of n is x of n convoluted with h of n. In transformation, if we apply the transformation, since convolution in time domain, it is multiplication in the frequency domain. Y of omega will be x of omega into h of omega, where h is called as frequency response. H of omega is the frequency response of the system. An LTI system is completely characterized by the frequency response. All the linear time invariant systems are characterized completely by its frequency response h. The above equation provides an alternative way of viewing the behavior of LTI system, so that we can view the system as operating in frequency domain on the Fourier transform of the input and output of the signals. The frequency spectrum of the output is the product of frequency spectrum of the input and the frequency response of the system. So this thing should always be remembered before discussing the LTI system. And next, in general case, the response H is complex valued function. Often we have H of omega in terms of magnitude of H of omega and argument of arg of H of omega. So the quantity of H of omega is called as magnitude response of the system. Similarly, argument of H of omega is called as phase response of the system. So trivially we can write y of omega in modulus as modulus of x of omega into modulus of h of omega, and argument of y of omega to be argument of x of omega plus argument of h of omega. So always do remember the magnitude of x of omega into magnitude of h of omega is in product for the spectrum, whereas the argument of x of omega, it is plus with the argument of h of omega for obtaining the argument of y of omega. So that is what is given here. The magnitude spectrum of the output equals to the magnitude spectrum of the input times the magnitude response of the system. Similarly, the space spectrum of the output equals to the phase spectrum of the input plus the phase response of the system. So very important things to be noted here. Similarly, it is a real valued function. Modulus of h of omega is equal to modulus of h of minus omega, and argument of h of omega is equal to minus argument of h of minus omega. Since the frequency response is going to be simply the frequency spectrum of the impulse response h, and h is real, we will obtain this as discussed earlier. H of omega is a even and the phase of the response is going to be odd. Argument of h of omega will be always odd, and modulus of h of omega is even. The block diagram representation, as discussed earlier, x is my input variable, h is the transfer function, and y is the output variable. So this is how the block diagram representation is given. Now we will discuss about the interconnection of LTI system. The series of interconnection of LTI system with the frequency response H1 of H1 and H2 is given by, when two cases are again possible here. One, it may be series interconnection, and another it may be parallel interconnection. So H1 of H of n, H2 can be equivalently written as H1 H2 in multiplication, and here it is H1 parallel with H2, H1 plus H2. So you have to remember this terminologies always, so which can be used for solving problems as well. LTI systems and difference equation. So many LTI systems of practical interest can be represented using nth order linear difference equation with constant coefficient. So the same formulas can be applicable, and here input x and output y, that is characterized by an equation. Summation k is equal to 0 to n vk y of n minus k is equal to summation k is equal to 0 to m ak x of n minus k. So as we know in general, we can write h of omega as y of omega by x of omega, which is equal to summation k is equal to 0 to m ak e to the power j omega whole power minus k divided by summation k is equal to 0 to n vk e to the power j omega whole power minus k, and again which is equal to 0 to m ak e to the power minus j k omega divided by summation k is equal to 0 to n vk e to the power minus j k omega. So the numerator and the denominator h polynomial is in e power minus j omega. So h is a rational function in the variable e to the power minus j omega. So please do remember this two terminology. Omega is in radian, and it is between 0 to 2 pi for the discrete time interval. This is the different of capital omega, where it is been from minus infinity to plus infinity. Note always that x of omega is periodic. So this all things to be noted before solving any kind of problems in discrete time Fourier transform. As discussed earlier, we will first have a recap of the transform pass before moving on to solving the gate problems. So quickly to summarize, this was a common Fourier transform pair, x of n, del of n and x of omega will be 1. Del of n minus n naught e to the power minus j omega n naught. X of n is equal to 1, 2 pi del of omega e power j omega naught n, 2 pi del of omega minus omega naught, cos omega naught n, pi del of omega minus omega naught plus del of omega plus omega naught, sin omega naught n minus j pi del of omega minus omega naught minus del of omega plus omega naught. U of n, again this x of n formula, minus u of minus n minus 1. It is minus pi del of omega plus 1 divided by 1 minus e power minus j omega. A power n u of n modulus of a less than 1. 1 divided by 1 minus a e power minus j omega n. Similarly, minus a power n u of minus n minus 1 for mod a greater than 1. It is again 1 divided by 1 minus a e power minus j omega. Similarly, all the other cases, please do remember this transformation pair, so which will be useful for solving the problems. Now we will try to solve problems which is asked in a gate previously. So the question number 1, x of n is equal to 2 times del of n plus 2 minus del of n plus 1 plus del of n minus del of n minus 1 plus 2 times del of n minus 2 with the Fourier transform x of omega. Then the value of x of omega at omega is equal to pi is what? So this is what the question is asked. As we know earlier, we can rewrite it as x of e to the power j pi, x of e to the power j pi, which is equal to summation n is equal to minus 2 to plus 2, minus 2 to plus 2 x of n into minus 1 whole power n. I am just going to substitute all these values. Just take this alone. So what I will have, the amplitudes around 2 plus 1 plus 1 plus 1 plus 2. So this is what I end up with. So if you add all these things, so 2 plus 1 3, 3 plus 1 4, 4 plus 1 5, 5 plus 2 7. So the answer is going to be 7. So very simple, but this problem is asked in the gate. We will see the next problem. A discrete time signal x of n is given by x of n is equal to minus 2 whole power n, 0 less than or equal to n less than or equal to 3, 0 elsewhere. If Fourier transform is x of e power j omega, then the value of the integral minus pi to plus pi modulus of x of e power j omega the whole square d omega is what? So can someone try to find this and give me the answer? We will wait for a couple of minutes. Try to solve it. So similar procedure you are going to use. I am giving you the formula alone. Just use the Pascal's relation. So which will be equal to 2 pi summation n is equal to minus infinity to plus infinity modulus of x of n the whole square. Just use the Pascal's relation. Very simple. Try to give the answer. Solve it. We found the answer. Just apply Pascal's relation. 2 pi it's common. You can use modulus of x of n the whole square summation. For the first case, it is going to vary from 0 to 3. So if you put 0, modulus of x of 0 the whole square, you will have x of 0 value. When you substitute anything for 0 is going to be 1. So first term is 1. Second time when you put 1, I will get my minus 2 whole power n the whole square. So 2 square is 4. Second 3 we will have 2. So 2 square is 4. 4 the whole square you will have 16. Then next value is 3. So minus 2 whole power 3 is 8. 8 square is 64. So we will be adding all these things. 1 plus 4 plus 16 plus 64. So the answer is going to be 175. So very simple. Minus pi to plus pi, x of e power j omega the whole square d omega 2 pi summation n is equal to minus infinity to plus infinity modulus of x of n the whole square 2 pi modulus of x of 0 the whole square plus modulus of x of 1 the whole square plus modulus of x of 2 the whole square plus modulus of x of 3 the whole square. Since the question given is minus 2 whole power n, minus 2 whole power n, I am just substituting here and I will get, when I put 0, it is anything for 0 is 1, so I will get 1. Second case when I put 1, I will have 2, 2 square is 4. Third case when I put 2, 2 square is 4. So again the 4 square will be 16. Similarly 2 power 3 is 8. 8 square is 64. You can add all these things. When you add, you will end up with 175. We will move to the next question. Is it clear? Any doubt on this? Consider a signal input single output discrete time system with x of n as an input and y of n as output, where the two are related as y of n is equal to n into modulus of x of n for 0 less than or equal to n less than or equal to 10, and x of n minus x of n minus 1 otherwise. Which one of the following statement is true about the system? It is causal and stable. It is causal but not stable. It is not causal but stable. It is neither causal nor stable. So this we have seen in the first unit itself. Very simple. Since the present output does not depend upon the future values, the input system is causal, and also for every bounded input that produces a bounded output, so the system is stable. So do remember here we do have it as modulus of x of n, n into this, where n is a finite value. The same case if they have given for n greater than 1 or n greater than 10, something like this, definitely we will have the value to be infinity at one given point, and that point it becomes infinite, so that system becomes astable. So remember this a lot. Let h of n be the impulse response of a discrete time linear time invariant filter. The impulse response is given by h of 0 is equal to 1 by 3, h of 1 is equal to 1 by 3, h of 2 is equal to 1 by 3, and h of n is equal to 0 for n less than 0 and n greater than 2. Let h of omega be the discrete time Fourier transform of h of n, where omega is normalized in angular frequency in radians, given that h of omega naught is equal to 0 and 0 less than omega naught less than pi. The value of omega naught in radians is equal to 1. So this problem is a fill in the blanks type of problem. So first from the question you can try to write 0 to 2. They have given n is going to vary between 0 to 2. So it means I will have 0, 1, 2. 3 values I will have, and they have given you the coefficients. So it is 1 by 3 del of n, 1 by 3 del of n minus 1, 1 by 3 del of n minus 2. So this is given, and I have written that too. And the next thing is, by the formula x of e power j omega is given by 2 pi by n summation k is equal to minus infinity to plus infinity del of omega minus 2 pi k by n. So we know that h of e power j omega, when we apply the transformation for this case, we will have 1 by 3 e power j omega into 1 plus I have e power j theta plus e power minus j theta. So that 2 combined I can rewrite it as 2 cos omega. Now h of e power j omega naught is equal to 0 for 1 plus 2 cos omega naught is equal to 0, and cos omega naught is equal to minus 1 by 2, whereas omega naught will be 2 pi by 3. So 2 pi by 3, we are asking it in terms of radians. So you can just calculate and check, it is 2.10. So always approximate it to be 2 decimals. We will move to the next question. An LTI system with unit sample response h of n is equal to 5 times del of n minus 7 times del of n minus 1 plus 7 times del of n minus 3 minus 5 times del of n minus 4 is what filter they are asking? Low pass filter, band pass filter, high pass filter and band stop filter. So this thing can be found just by checking h of e power j omega, then you try to substitute omega is equal to 0 and omega is equal to pi, you will get some values. With the help of that you can check which type of filter it is going to be. So as discussed in the previous problem, what I do was I have taken h of n first, then I am applying the transformation, so I will get 5 minus 7 e power minus j omega plus 7 e power minus j 3 omega minus 5 e power minus j 4 omega. So I put omega equal to 0, automatically here it is 5 again, minus 7, e power 0 is going to be 1, e power 0 is 1, e power 0 is 1. So 5 minus 7 plus 7 minus 5, so it becomes 0. I am just substituting omega is equal to pi. When I substitute omega is equal to pi, again what happens? Same case is going to occur, e power minus j pi, e power minus j 3 pi, e power minus j 4 pi. So e power minus j pi is minus 1, e power minus j 3 pi is again minus 1, and this is also 1. Just substitute it, I will get answer to be 0. So system is going to attenuate from the low and high frequency, whereas passing the mid frequency. Because since this both have become 0, directly we can come to the conclusion it is going to attenuate for the low and high frequency and passing the mid frequency. So which filter is going to do all these things? It is a band pass filter that do all these things. So the answer is going to be band pass filter. So very simple but interesting question to solve. They have asked you to find the filter. So this is one of the application where our discrete time Fourier transform can be used to check whether the filter what filter we are going to use for these cases. And the next question, let x of n is equal to 1 by 2 whole power n u of n, y of n is equal to x square of n, and y of e power j omega be the Fourier transform of y of n, then y of e power 0 is what? Very simple. To give you a frank answer, directly you should be able to solve this. What is given? Just try to apply the transformation. When I apply a power n u of n, what I will get? 1 divided by 1 minus a is e power minus j omega. What is in place of a? It is 1 by 2. So I will have 1 divided by 1 minus 1 by 2 e power minus j omega. But what is given in the question, instead of x of n, they have given it as x square of n. So when I do square it, I will have 1 divided by 1 minus a square e power minus j omega. A square is 1 by 4. So I will get 1 divided by 1 minus 1 by 4 e power minus j omega. They are asking you to find at e j0. So it means that you are going to substitute instead of omega 0. So what I have got, 1 divided by 1 minus 1 by 4 e power minus j0. E power 0 is 1. So I will have 1 divided by 1 minus 1 by 4. Just try to solve it. We will get 4 by 3. So very simple problem. But if you remember the pairs that I was discussing earlier, it is very simple to solve this kind of problems. Next question. A signal x of n equal to sin omega naught n plus 5 is the input to linear time invariant system having a frequency response h of e power j omega. If the output of the system a x of n minus n naught, then the most general form of angle of h of e power j omega will be option A minus n naught omega naught plus beta for any arbitrary real, Option B, minus n naught omega naught plus 2 pi k for any arbitrary integer k. Option C, n naught omega naught plus 2 pi k for any arbitrary integer k. Option D, minus n naught omega naught phi. So for this case, what we have to do? I'm just trying to rewrite the things. Very simple. They have given you output of the system is Ax of n minus n naught. From this, you can say that y of n is equal to this. Next, from this, if you apply the transformation, you will get y of e power j omega. So this can be obtained. Similarly, you know x of n. We also have h of e power j omega. Since they have asked you the angle, we know h of e power j omega in general, which is given by y of e power j omega divided by x of e power j omega. So this is also a known factor to us. So by this I can come to a conclusion. When I apply the transformation here, I get a n minus n naught translation property e power minus j omega n naught is what I will get into x of e power j omega. You bring this x of e power j omega down. So y of e power j omega divided by x of e power j omega will be a e power minus j omega n naught. Now what is asked? Only angle is asked. Angle is going to be minus omega n naught. Minus omega n naught is the angle. So for any LTI discrete time system, phase and frequency of h of e power j omega are periodic with the period 2 pi. This is also a known factor to us. So in general, I can rewrite it as minus omega n naught plus 2 pi k. So which is the answer that is having this? Minus omega n naught 2 pi k. So the option is going to be B. So very simple problem. We'll go to the next problem. The impulse response h of n of a LTI system is given by h of n is equal to minus 2 root 2 for n is equal to minus 1 to minus n, 4 by root 2 for n is equal to 2 comma minus 2, 0 otherwise. If the input to the above system is the sequence e power j pi n by 4, the output is what they have asked. So for this problem, we have to first find h of n. You rewrite h of n properly, then we can go for finding y of n using convolution. This is our x of n, this is our h of n. Take the convolution, and with the help of convolution we can find what is y of n. Try to solve it. Y of n will be x of n convoluted with h of n. I am just going to apply convolution for this. Formula for convolution, as everyone knows, summation minus infinity to plus infinity x of k into h of n minus k. So we have got y of n to be, you have got h of n, you have got x of n. Try to substitute. So I will give you the answer. Just check here. X of n is e power j pi n by 4. H of n is 4 root 2 del of n plus 2 minus 2 root 2 del of n plus 1 minus 2 root 2 del of n minus 1 plus 4 root 2 del of n minus 2. So I am using the convolution formula, minus infinity to plus infinity x of n minus k h of k. So the limit is going to vary between minus 2 to plus 2. I just substitute it. So what I will have when I put upper limit first 2 here, so I will have n minus 2 h of k. Similarly h of 2. Similarly substitute 1 n minus 1 h of 1. Then 0 n minus 0 h of 0. Put minus 1 h of n plus 1 h of minus 1. Then put minus 2 x of n plus 2 h of minus 2. Just substitute the values from the above. We will get 4 root 2 e power j. Some terms we will have. Just try to solve all these things. And we will end up with y of n to be minus 4 e to the power j pi by 4n. Just try to solve this and then check it. So very simple problems of DTFT. We should all remember all these things. So references. So I have used the lecture slides of Michael D. Adams sir, Professor Palkov. Very useful lecture slides I have taken from here. And the basics concepts is taken from the Signals and System Oppenheim textbook. And we have taken few gate problems from the Noida publication, Archicanodia. I have also referred with the MIT Open courseware, ACE Engineering Academy, ADC, and Dr. N. Balaji JNTU sites were also be referred. So I thank all the above references, authors, and I take credit to give them where I have used their text for preparing this course material. Thank you. If any doubts, please do text me. We will solve it. I will try to address the query. Thank you all.